Okay, so I guess we get started. Welcome to the QuMat seminar today. It's my particular pleasure to introduce today's speaker, Kamran Behnia from Paris. Kamran is originally from Iran. He did his actually most of his research and of his education was in France, or at least in French-speaking places. So he did his PhD, master PhD in Grenoble, went to Geneva for a postdoc, and then after that he went to Paris, first to Orsay, and now to ESPCI, where he has been since. Kamran Behnia is known for working on, I would say, very classical condensed matter problems, usually having to do with elementary properties of metals, and this is also something he will talk about today. So thanks for coming.
Thank you, Lars. It's a pleasure to be here. It's my first actually visit to Utrecht, but I'm very happy to be here, present this result, and it's also fun because I have old friends here. And well, the subject I'm going to talk sounds a little strange. I'm not going to talk about something very exotic. Heat carrying sound in liquid helium-2 sounds a little strange, but you are going to see that this is more common than you would believe. And of course, we are coming back to Fermi liquids and non-Fermi liquids. So maybe before I should begin by presenting my colleagues, many of these young people who are here are no more in Paris, but I had a chain of Chinese students, beginning with Zhang Weizhu in Wuhan, and then it continues to have this. Hopefully, it will continue. I don't know. I have a younger colleague who's a permanent researcher in Paris, Benoît Fouquet. I would like also to acknowledge and then talk about helium-3. Kostya Trashenko is a theorist colleague in London, and other people who see we have collaborations, many were in Japan, in Brazil, Switzerland, and elsewhere. So before beginning my talk, just to make you sure that, because I hope it will be simple and understandable, but I would like to say that actually it is about a vacancy about our knowledge. When we talk about thermal conductivity, I have been measuring thermal conductivity. Lars mentioned I was in Grenoble measuring thermal conductivity of UPD3, an unconventional superconductor. So I've been doing this kind of business job for 30 years. But I didn't know this curve, which is thermal conductivity of water. See, this is QuMat. We are doing quantum materials. I don't know if water qualifies as a quantum material. The fact is, I'm going to ask you a question. What is carrying heat here? Actually, we know the answer here, ice. So you see, these are first order phase transitions. You have recognized that ice becomes water and water becomes vapor at these temperatures, by heart. We know also the answer here. Water vapor. What carries heat? Molecules. So these are kind of stuff we learn in university at some point. But if you asked me 5 years ago, what carries heat here? Actually, I would have scratched my head and maybe I don't know if I would have come. Of course, the answer is no. The answer is no, but somehow buried, not in something that you learn in a condensed matter physics. And this is a pity. So this curve is not published yet. It will be published somewhere in some review or part, but this is nothing. So this is something that actually I gather. But I will come back to this curve during my talk. I begin with this just saying that actually, yes, as Lars said, I'm talking about very elementary physics, but somehow not discussed. What I'm going to begin my talk with something that you are more familiar with, is that, okay, forget thermal resistivity, chi-square resistivity is a typo. We all know that Fermi liquids are well understood as the resistivity are following something like this, a chi-square resistivity which comes from electron electron scattering. And the reason is basically if you have a Fermi liquid, you have a system of fermions. The Pauli exclusion principle works for each of the two colliding electrons, so you use it twice. The phase space is going to grow like kBt to the power of 2. divided by Fermi energy to power. Now, one thing that experimentalists know, more or less, is that this is very hard to be seen in copper or aluminum, the most ordinary elements, metallic elements you can think of, but it is easy to see either in correlated metals or in dilute metals. These are curves by different people during different times. You see bismuth, 1969, graphite, 1984, WT3, 1995, glutamate. These two guys pass correlated electrons. You cannot explain normally their properties without invoking Coulomb interaction between electrons. These guys happen to be weakly correlated, but because the density of electrons is low, you still see this is T-square resistivity without subtracting anything. So what matters is not electron phonon scattering. Now, you may have thought about this, but you see, if two electrons bump to each other, even if the phase space argument holds that the scattering rate should be T squared, you may ask yourself the question, why should there be any decay in the electrical current? Collision conserves momentum. The two guys at the initial state and the two guys at the final state end up by having the same amount of momentum. So why should there be any resistivity? The answer is, again, is that there are two ways. This is not discussed in detail, but now you begin by thinking about this. I will say in one moment why. The first person who proposed this T-square resistivity was Bobber in England. Almost simultaneously, Landau and Pomeranchuk proposed another mechanism. Both are up to this result of T-square. In the first case, the whole idea is that, yes, you can have electron-electron scattering, but if you have two reservoirs of electrons, for example, a compensated system, then there is a bottleneck between these two guys, because at the end, what is going to be the source of momentum loss is the reservoir, the thermal mass of hormones, but there is no guarantee that these two reservoirs are coupled to the phonon mass in the same way. So the bottleneck can govern the other way, which is actually something which makes sense because you don't even need to invoke this multiplicity of reservoirs, is to invoke umklapp. An umklapp collision is when you have two electrons colliding to each other, like K1I and K2I, and you create another situation in which the difference between the final states and the initial states is larger than your Brillouin zone bits. And in that case, you are going to lose some momentum to the lattice. Since most metals we know belong to this category, it has not been a big source of attention. Okay, actually, the reason I became interested in this question was that in 2015, we were looking at the strontium titanate. So strontium titanate, for many reasons, it is very interesting. It is a superconductor. It is a quantum paraelectric. It has a variety of interesting properties. For our purpose, what was interesting was it is a banal band insulator with a very small Fermi surface when it is doped. So the Fermi surface is at the Fermi, at the center of the Bridgman zone, and you see this is the size of it in the units of the Bridgman zone. So you have 5% of the width of the width. It's very small. There is no umklapp happening here, and this Fermi surface has been found experimentally, and it is in extremely good agreement with what has been calculated by our theorist friends. So at initial weakly correlated system. So what we found is that you can find a T-squared behavior. You can change the carrier density by more than 2 orders of magnitude just by changing the number of electrons. This is something which should not happen because we have none of the two mechanisms I mentioned which work here. Now, this was in 2015. And of course, it looked like a heresy. So some of our theorist friends, like Dimitri Maslow, they went and found solutions to this puzzle. The solution to the puzzle they proposed is that this system is actually very interesting because it has strange phonons, soft phonons, and there are mechanisms to have T-square resistivity when one electron is colliding with two phonons, two soft phonons. Why not? The problem is that strontium titanate is not alone. Since then, there were other systems. So this is bismuth 2, oxygen 2, selenium. I'm not going to talk about this. This is an interesting system, but it doesn't have the soft phonons of strontium titanate. Actually, you have other systems like zirconium tellur 5. There is a fourth system. I'm not going to talk about it. The statement is the following. It looks like if you take a three-dimensional metal and make the Fermi surface small enough, when umplab is forbidden and there is only one reservoir, you still get this T-square resistivity you cannot get rid of. The second question is, what's the magnitude of A? So I grew up in heavy fermion community, and there is a very successful empirical plot. We're going to pass 2 minutes about this. So it is called Kadowaki-Woods plot. Kadowaki and Woods in 1986 made this empirical diagram where you see this T-square electronic resistivity versus electronic specific heat gamma. So you see, when you are traveling in this direction, you are having electrons heavier and heavier, and you see that these two guys correlate with each other. Actually, Kadowaki and Woods had the idea of scaling from Rice, 1968, who did the same thing for elemental metals. You see, this is a log scale. So here, gamma, this is a linear scale. So this is gamma square, and the number here is much smaller. So you are in this diagram. And the point was that maybe there is a particular scaling for the strongly correlated system. Now, just why this works, if you look at the specific heat, what I'm putting here is the expression for the specific heat of a free electron gas. You recognize the Fermi energy, the carrier density, and if you compare these two guys and admit that your A is somehow connected to the Fermi energy, you see that this scaling should work. If you have basically of the order of 1 electron per atom, and you expect, even if you don't know what is the source of this dissipation, that if the two are correlating with the Fermi energy, there should be a correlation between the two. And this should not work with when n is much smaller than 1. And actually, this is what I found in my review paper, that for some reason, maybe it didn't work. In Rice's paper in 1968, actually, bismuth, graphite, and antimony, which are very dilute metals, they don't work actually. And this was the reason actually some people were suspicious about why bismuth is in bismuth, even this large A is coming from electron-electron scattering. But if you put A as a function of EF, you see that it works. This is empirical, but it works. And now I can make the following statement. If you have any favorite three-dimensional metal, we can put it in this extended Kawhi-Woods scaling. If you know the Fermi energy, so you know the Fermi energy, either you take specific heat and take the carrier density, or you do quantum oscillations, or you calculate it. It's something which is accessible by experiment. And of course, A is something that you measure experimentally. So it is a curve where you have one experimental point as a function of another experimental point. So we have a very good empirical plot. The problem is that we don't still know why some of these guys are on this plot. It cannot come from umplab. So there is a, let's say, hole in our understanding. We still don't understand in the Fermi liquid, let alone for strange metals, why electron-electron scattering is giving you a T-square resistivity that we can empirically predict if we know the Fermi energy. So these are two open questions, and this is the motivation of my talk. The first is why you can always predict your T-square resistivity
if you know the Fermi energy, and why it persists without Unclap. Okay, my expertise is thermal transfer. So all of this was like an aperitif for what we are going to do after. So thermal transfer is more difficult to measure because, you know, if you measure electrical conductivity, if you are an insulator, you know that you can be completely protected from any leak. Heat can travel in a much more complicated way than electricity, so it is harder to measure. But let's come back to this. These two are connected. There is a method by Bridgman and France, discovered in 1853, which survived the quantum revolution. And not only it survived, it became something that you won't want to violate in zero temperature. Means that if you measure your thermal conductivity, you divide it by electrical conductivity and temperature, you get this number, which is closely related to the two fundamental constants, the Boltzmann constant and the charge of electron. Now, why this is important for our situation? Because actually there is also T-squared thermal resistivity. This T-squared thermal resistivity has been measured. This is data by Wagner, and this is the data by Typer's group by Jean-Pierre Farinot on cerium-rhodium-indium-5. Tungsten, a weakly correlated system, cerium-rhodium-indium-5, a strongly correlated system. Now, what you see here is that both are expressed in the same units. You know, taking this fundamental constant factor in take-one form, you see that both data sets extrapolate in the same value at zero temperature. This means that if you look at the intercept, the Bridgman-France law is perfectly obeyed at zero temperature. Both follow a T-square behavior, but the thermal slope is larger. And this, again, is not a big discovery. This is known. You can even find some discussions of them in textbooks. It's because you have inelastic scattering is more efficient for thermal channel than for electrical channel. So up to here, nothing surprising, but there is an interesting turn about it. This can also be measured in dilute metals. This is our work on antimony. This is on work on we did that also on strontium titanate, and we can again find the T-squared thermal resistivity obeying, of course, the constant is not exactly the same, but again it follows the same extended Kadowaki-Woods ratio. Okay, why I put it in my plot? Because the big difference between these two guys is that you don't need unclapped events. So something which was mysterious when it was looked from the electrical channel, it is no more mysterious. And we have a good proof of it. So I'm going to go back in time. Let's ask ourselves, where does this Fermi liquid theory come from? Actually, it was conceived by Landau in 1950s, trying to explain what happens to helium-3. So helium-3 is a very interesting system in which the collisions between fermions also goes like T-2. This is the reason it has a viscosity which increases dramatically, and at 3 millikelvin, it has a viscosity as large as Olivor. Now, it changes our subject of discussion, because one can say, so how about thermal resistivity in helium-3? And the reason it has never been considered before is that people who were measuring helium-3, so this is the data by Greywall that I'm going to present in my talk. The way he plotted his data in his community is that kappa is proportional to 1/T, and this is the Fermi liquid behavior there. For a metal physicist who is interested in electrical resistivity, it is exactly equivalent to say that WT, which is the inverse of kappa divided by temperature, is proportional to T squared. So these two communities did not talk to each other in the sense of comparing their data. So if you put now helium-3 with metals, so you see, this value is much larger. This is what we call V, the inverse of thermal multiplied by temperature. Of course, the Fermi temperature of helium-3 is much smaller than these guys. The density is comparable with a dense metal, but the mass, we are talking about the real mass, not the effective mass, is the mass of 3 protons. So 5,000 times the mass of the electron. But you see that this guy is actually on the same plot. So there is no reason to doubt at the moment that this physics and this physics share some common features. We think we understand this physics. There is no reason not to extrapolate this physics to this physics. Now the question is why we don't understand still the electrical transport. Normally thermal transport is more exotic, more problematic, theoretically also to be calculated. But it looks like the big mystery is why the electrical transport continues to obey roughly the Bridgman-Franz law in this context. There is another thing here. The quadratic correlation has very strange, factor. There was not obvious to see how to translate ohm, centimeter. Here, actually, it is obvious because this factor is nothing else than h bar EF squared KF. These units, it gives you material per watt. The only thing which happens here is a prefactor of the order unit is higher. I will come back to it. Okay, and helium-3 is believed to be understood because you have Landau parameters. There are textbooks, several hundred pages to explain almost everything about helium-3. Normally, it is a solved problem. Is it a solved problem?
Sorry.
Yes.
So here you were having all these heavy fermions, and then the other materials like bismuth. Where are the other materials like, I don't know, oxide, high TC, and so on?
Well, you can put them. The problem is that we don't have enough data points. But okay, I come back now here. Everything. So this was only thermal data, which is great. But if you are interested in electrical data, so here is YBCO 11%. Here is strontium ruthenate. If you are interested in these are many of these guys are heavy fermions. So anything, now my claim, I make this a strong claim. Give me anything, look, 3 weeks ago, we were discussing with a colleague in Caen, ruthenium dioxide. It is the altermagnet candidate. The first question, where is the T-square? Give me your data. Send us our data, RuO2 is conversion. So you have both gamma. So anything we know of, if there is a T-square in the system. So there are people, I have not done it. So people in India who have put twisted binary graphene on this curve. I don't know how they measure their Fermi energy. So you just need to know, because you know that there is a T-square term in twisted binary graphene. So you can measure A, but then you should also be able to know what is your Fermi. So, but you see, this is mysterious because we have no good microscopic understanding of what's going on. But T-square thermal, I'm not going to enter it, but it's basically, there's no need for umklapp. If you know the mass, you can explain. Okay, but now I'm going to enter actually the core of my talk. So this was a situation like a few years ago, 2 years ago, and we were saying, okay, everything is understood in helium-3, and we should just extrapolate what is happening in helium-3 to metals. Actually, that was wrong. So there is this very nice paper by Tony Leggett, published in 2016, and actually I knew about it only in 2020. It's in Report on Progress in Physics, and I think the editors asked Tony Leggett something like this: look, there is one Fermi liquid that we understand very well. Explain us to us, because and he wrote this paper, very nice, and one of the things he says in this paper is a kind of disclaimer. One thing should be emphasized at the start. When we say that we have a semi-quantitative understanding of the properties of liquid helium-3, this claim is really justified only over a rather small region of the parameter space. So even the best understood Fermi liquid seems to be, so how broad is this range? He says, well, you should go to much below TF. You should have a cube much smaller than KF, and you should have a frequency much smaller than F over H. Okay, how small? Said, well, you should go below 100 millikelvin. The degeneracy temperature of the helium-3 is something about 2.5 K. Okay, so it's like you should go to something like 25 times smaller than Fermi. But it's a little surprising. But then you look at the data and you see that even this understatement is an understatement. The situation is worse. So here is the data. Because this is actually, so the gray one, so this is the time, people in Bell Labs could pass like 3 years, 4 years, 5 years, I don't know, to write a paper just about thermal conductivity normal liquid helium-3. And the data, so he was not the first to measure helium-3, so there are many papers before, but he closed the field in the sense that nobody could do better. Now, the Fermi liquid region, kappa proportion of 1/T, is where your data is following this. So as you can see, A is at ambient pressure, the molar volume is high. So it is 1/T, but you are elevating, then it becomes less and less. So actually, okay, below 20 millikelvin, maybe you have this guy. The second point, so it's like not 20 times, maybe 50 times. No, but the deviation happens very early. Now, even at the fraction of Fermi temperature, you have this strange law, which is kappa to the power of T to 1/2, which has never been discussed. Somehow, this story was closed because this matches Landau's theory, but that part, which you can see here, which is actually mentioned in Gregor's paper, has remained unexplained. Okay, I would say that after our data was published, our Russian friends told us that there was one guy in London Institute back in 1980s who said, well, I have a theory for this. This is the only case where there was an explanation for this proposed discussion. Actually, the problem went out of fashion. So, how come? Where does it come from? So this is where, So, I have a friend, Kostya Trachenko, who is an expert of classical liquids. He is in London. He has written this book, and we had a discussion because we met in a conference and we began discussing. He was talking about classical liquids. I said I'm interested in quantum liquids, and he told me, "Okay, explain to me this Landau," because of course he's Ukrainian, but he knew that in Soviet Union there were two schools, one by Landau, of course the most prestigious, but the other school by Frankel. And Frankel was the guy who was interested in liquids, and Landau was always saying, no, liquids, it's not very interesting, it's not quantum. So there was a kind of debate about what is interesting. And so I would say yes, we know that in Landau's Fermi theory, you have quasi-particles which collide with each other, and it goes, wait a minute, what are we talking about? It's a liquid, the collision, there is no collisions in a liquid. In water, you have neighbors. Collision is something which happens in gas. And actually, if you read, I went back and read Landau's papers. He makes a distinction between a gas of quasi-particles and the Fermi liquid theory. This is what we now summarize the Fermi liquid theory, the quasi-particle part. The second part was the sound part. So now, why this is important? Because you see, what I am showing here is the pair correlation factor. The pair correlation factor, G, is a simulation for, I think, argon. So any system, if you are in a liquid system, you see that you have oscillations. In a gas, you don't have oscillations. In a crystal, you do have oscillations. You have more oscillations because your oscillations are deeper. What is happening is that if you are at some position, imagine that you are an atom. Does anybody care about you being present at this place? If you are in a gas, the answer is no. Nobody cares. So this is what you get, the red one. If you are in a crystal, of course, if you are in a crystal, if you are here, by the periodicity, there is some peak. because people, atoms are going to move in places which correspond to yours. If you're in a liquid, this memory survives. So you have neighbors, they change. And the language of collision is proper when you use a gas. So what this matters, because actually in liquids, you have phonons. These are neutron scattering measurements done on the liquid meal at 32 K. And you see some of the things that I didn't know that there are a bunch of people who are measuring these kind of things. Collective excitations in a liquid, which are called phonons, okay? There are phonons with some, it's not very beautiful because it looks very disordered. The disorder is natural because the atoms are not keeping their place. But you have a dispersion and you have something which very much looks like a
roton.
So this is actually a misnomer because a roton is not a property of superfluid helium superfluid. Any liquid you look at, you will see something, and this is where you have this kind of this. So you have collective excitation. So here is the whole thing is that now I can answer the question I asked. What happens in a liquid like water? So there is a guy called Bridgman. Maybe you have seen the Oppenheimer movie. Bridgman was, and he doesn't appear in the movie, Bridgman was Oppenheimer's PhD advisor. And I think he was not happy and he didn't do any experimental things. But Bridgman is famous because of pressure, because of a relation for Nernst effect, and in liquid community, he's famous for this formula, which is very simple. He stated that basically the thermal conductivity of any liquid is R Kb n to the log 2/3 and sound velocity. And actually, this is the sound velocity. It describes the velocity, the thermal conductivity of water. So you see that there is a temperature dependence. It's not very large, but if you want to have the order of magnitude. So if you want to compare water with alcohol, you should look at their sound velocity. So, this is methanol. So the liquid community people use this formula to know more or less. So they try to perfection this. So these are, Bridgman formulas, modified to have some difference. But at the end of the day, it boils down to the following simple formula. I will come back to it in a minute. So there are formulas.
What is R here? Is it just some feedback?
Just some number.
Exactly. This is a number between 2 and 3. So you see, if you remember,
Be specific as well.
exactly. So basically, this is a simple formula. This is actually okay. I am going to talk about it in 1 minute. This is Motlopher radial formula for formulas. So the mean free pass is the interatomic distance, and this is the specific heat. You know that for solid. So this is this guy. I don't remember who was said that I have been teaching solid state physics for 30 years, and I had this nervous worry of a student asking me between the course on specific heat of gases and specific heat of solids, what is the specific heat of liquids? Nobody asked this question about 30 years. Of course, because you see, for gases, you have 3 divided by 2. For solids, you have 3. So for liquids, the problem is that we don't know the answer. But anybody who would think a little would say it should be somewhere between 1.5 and 3. But this is again the problem of why liquids were not taught or touched. First of all, you don't see that much quantum mechanics there. Second, it looks like complicated and not fascinating like harmonic oscillators in solids or perfect gas in gases. It's very empirical. But the story is that actually Bridgman had solved problem empirically, and it was. So now let's become a little more to this, because actually I have been talking about thermal conductivity, but let's look at thermal diffusivity. These are very intimately linked quantities. This one, thermal diffusivity, is the solution of, not the solution, is a parameter in the equation which describes the propagation of heat, the heat equation, the diffusion equation. It has for units meter square divided by centimeter. And thermal conductivity is actually what appears in the Fourier's equation. This is static, there is no time dependence, there is a time dependency. And actually, you can show immediately that these two guys should be related to each other, D and kappa, by specific heat. So if I divide my thermal conductivity by specific heat per volume, I should get my diffusivity if I have the two sets of data. And now, I have done this for water, this becomes better to see what's happening here. So actually, it is very interesting. It is not a joke that water is a quantum material, because everything is in the eye of beholder. Look at diffusivity of ice. What you see is that the diffusivity of ice is 3 times sound velocity squared times the Planckian time. You have heard of Planckian time maybe recently either, but you don't need to go very far. Even in ice, you are seeing something which is actually discussed. So we saw this empirically, and Sean Hartnell and Musatov, they found an explanation. You can see this is not something, actually it was not observed before, but this is something that you can explain with like hands. Now, the water part, you see, what we are talking is that diffusivity of the system is of total 1/3 of ESA, which is basically multi-upper radial limit for phonons. It means that the phonons are there, but they are localized. They cannot move more than 1 atomic distance. And of course, the gas part, you have no more collective excitations. So here and here, you see the sound velocity is present. Here, the velocity is thermal velocity of individual atoms. And now, the story is interesting because what I showed you was water at ambient pressure. There is data on water when it becomes supercritical. Supercritical water is when, there is no distinction between the liquid and the gas. Thermodynamically speaking, you are in the same phase. But see, you still have a minimum. And actually, when we looked at almost everything which is available, any fluid in which the data is available on this NIST site, you can find that actually this minimum persists. This is something, this is really some experimental observation. So Kostia has an explanation. This is the whole idea that diffusivity cannot become smaller than a minimum value, which is basically velocity and distance. Your velocity cannot be smaller than your sound velocity. The distance has a minimum, which is the distance between 2 atoms. So there is some hand-waving way of understanding why there is a minimum. So you may say, what is the relation of this with helium-3? So in this context, having said all this stuff about classical liquids, let's look again now to the thermal diffusivity of helium-3. So here I'm plotting thermal diffusivity because it can be understood a little better. So what you are seeing again in this gray ball data is that there is a minimum. Now, if you compare this minimum with classical liquids of the same almost atomic weight, helium-4 and hydrogen. But look, these are under high pressure, sufficiently to be supercritical. The same minimum that you are seeing here is appearing. You see that the vertical axis has the same units. So this minimum is not very far from these two minimums. We can understand this. So I'm going to try to say how this comparison provides an explanation. Let's begin with the way we understand. So you are in presence of a classical fluid in the gas-like region. You cool it down. Thermal diffusivity should go down. Why? Because what is diffusivity? Velocity times mean free pass. Both of them are going to decrease with temperature. Okay, now I go to the quantum side. Here, you have a gas of quasi-particles. So Landau was right. You can explain the low temperature part if you imagine that what's going on is that quasi-particles bump to each other. You have a gas. No, the situation is reversed. You warm the system and the mean free path is going down. The velocity is constant. It is Fermi velocity. So we can understand why it is going down. Okay.
Can I
What? Yes.
ask a question? So if I'm not mistaken, helium should undergo the transition from superfluid at 2 points.
We are at 3 megapascal. This is 13. So I'm showing the data. Helium-3 at 0 pressure, or is very different. It has become superfluid at 2K, and you have a completely
So it's
different.
really due to the pressure that.
Yes, exactly. Yes. So here, it's the two cases are classical liquids with with a mass which is slightly different from helium-3, but under pressure. We got rid of all these quantum effects.
Yeah.
Now, let's ask ourselves what happens here to the minimum. Okay, here also we have an answer. The answer was, don't forget, you have sound. So as you decrease your temperature, at some point, you are going to have collective modes because the diffusivity cannot become smaller than velocity times the interatomic distance. So from here on, we have a phonon mode of transport. Even if you are in a supercritical fluid, because this is the liquid-like behavior of the supercritical fluid. This is the way people in classical liquids understand their data. So we come to this mysterious part.
So is it fair to say what happens is if you are doing a high temperature, I mean, you have phonons, but they're very short-lived, right? Vibrations die out, and then when you cool it down, everything then condenses in some sense. You give these phonons a longer lifetime mean free path. That the
Yes.
story.
Yes, it is correct. And since you asked this question, let me elaborate on that. You know, we are speaking to each other, which means that we are in an atmosphere where sound is propagating. You see, but if I light a candle here and I want to warm you up, convection will happen. Thermal conductivity is too weak. If we go inside water, so if you are in a fluid dense enough, then thermal conductivity can compete or even beat convection. So here, actually, the individual movement of, because as you said, because the system is not dense enough. So collective, propagation is too weak. But when this becomes weaker than V times Vs, sound velocity times the interatomic distance, the other guys take the lead. Okay, but you see, these 3 parts are all understood. The mysterious part is here, but we can make the analogy. The analogy, okay, here we are still in a quantum liquid, but now there should be some collective excitation because now your quasi-particles have such a short mean free path that they cannot compete as a mode of transport with this other mysterious quantity. Okay, so let me summarize. So we are suggesting a kind of revision in some, if you look at what we understand, is that you have a solid, insulator. Forget metals for one moment. You have an insulator. How do you understand thermal conductivity of silicon? Itinerant forms. How do you understand thermal conductivity of ice? Itinerant forms. Melt the solid. Your phonons become localized. And then when you go to the gas, then you can forget phonons at the mode of transport. Actually, this is the way now we can understand transport in a quantum liquid. We understand gas of quasi-particles. This is actually what Landau achieved. We can understand classical liquid because Bridgman has given us. But actually, any quantum liquid before becoming classical liquid gets out of this regime. How can this work? This is the missing part. Okay? So you see, actually, there is melting here, and here is the quantum classical crossover. Okay, very nice. You come with this. Well, we understood phonons should conduct heat in quantum liquid. The problem is that, okay, phonons have been studied in crystals, both at high temperature and low temperature, in glasses, and in classical liquids. If you look, none of them give you a T⁻². All of them give you something like T3, and all of this can be understood. Why? I'm not going around it, it's well understood, but the question is, how can we explain with a T⁻²? Okay, so what I'm going to give you is the first very simplistic hand-waving argument. You see, let's go back to this Bridgman formula, and let's try to go back to your student years and say, how can I make this? This is a classical formula, and I want to make it quantum. Okay, what is this? We discussed it first. Basically, this says that the thermal conductivity is the entropy density. You see, you have this R, which is between 2 and 3, N, which is density, and Kb. Then you multiply it by velocity, which is a distance. So N2 is just you have N times N to the power minus 1/3. How can I make this quantum? Well, you do what you learn in school. Entropy density, instead of having the equipartition, you multiply it by kBt divided by Tf. This is what we learn. Velocity, instead of having some velocity, I'm going to replace it with Fermi velocity. How about distance? This is the most controversial. Of course, we know the answer before to find it. So how about taking the distance as taking the Dubroy thermal length? Isn't it the length which governs the passage between quantum and classical? Okay, if we do this, we arrive to this formula. So you see here, there is something like 1.88. This is because you have pi to strange powers and 2 and 3. You end up by having k. But I want to. So this formula is saying that if you take the Bridgman formula, make it quantum, this very naive way, you find something in which actually there is no Planck constant. Strange, because this is quantum. It's because Planck constant here and here they go. They are going finally. There is one here. And here there are two h square here. H they cancel out. So you have a formula which only depends on the mass and density. Okay? Okay. We try to do a more serious thing. So one thing we have learned during the second half of the 20th century, thanks to Landau, is that, you see, the root formula can be re-expressed in this way. You see, you know this root formula, but if you write it in the way Landau wrote, which means that your conductivity cannot have any magnitude. You have the quantum of conductance times transmission, and you should count the number of channels. So you can get with this formula, where there is a mean free pass of quasi-particles, then with these strange numbers, 2/3 of kf squared p. And of course, we can do the same thing for thermal conductivity. The only difference is that the quantum of thermal conductance is not the same as quantum of electrical conductance. They are related by Bridgman-Cross law. And if you do it, this is less famous than this guy, but you find something as simple as that. Okay, what we can do now is to say, what would be the mean free pass of my collective excitation? So the simplest way would be just to replace A with this Dubroy length. Why this Dubroy thermal length is basically a quantification of how your Fermi surface is becoming thicker and thicker with temperature in the momentum space. Then you find this value, because the number of modes is exactly the same. You have the same amount of fermions in a Fermi sphere. If we do this, we find exactly the same thing that we found the other. So trust me, these numbers, 2.9 divided by 9, it comes to. So you have two ways. So I don't want to be fetishist. I just want to say, okay, we try, but can it work really? Let's try it with experimental data. So Greywald did his measurements in 1984. I told you that he finished his job. He finished the hardest part. 10 years after, Morphy and Mayer measured actual thermal conductivity at higher temperatures. They did it only at one pressure, at ambient, at saturating vacuum pressure. So actually, there is a mismatch between the two, but you see that it continues. And what I'm plotting here is not kappa, is kappa divided by T. To show the T minus 2 behavior, you see somewhere below 20 millikelvin, you have this gas of quasi-particle behavior, you have a deviation. So the formula we proposed, without any fitting, you just put the number. So N is the density of fermions in helium-3. M star is 2.7. The specific M3 is mass of 2 protons and 1 neutron. 2.7 is the specific data mass amplification. So you see that it is very close, but it is not perfectly there without anything. Now, we go one step further. If here it is T minus 2, and here it is square root of T, how about fitting the whole data in this range? So I'm showing the result. You see that for the whole temperature range, you can understand, you can explain the experimental data by a fit of two components. One is the square root of T, and the other is this T minus 1. So here is the plot of kappa divided by temperature. Here is the plot of kappa beta. This is the same data. So you see that the agreement is not perfect, but we didn't have any coupling. You know, a referee asked, but these two guys should couple to each other. Said yes for one, but this is why maybe our fit is not perfect. But we don't. But the whole point is that such a simplistic approach can give you an account of the whole data. Okay. We believe that we know the answer. At the same time, we don't understand really the answer. Because what does it mean? You know, because the two formulas, you know, the two ways I got the formula was somehow cheating. You know, you want to say, how can I get something which is a very reasonable way, and you get the right temperature depth and great. Now, I try to rationalize, but most probably it should be understood by competent people. So this is what we understood up to now. We have a Fermi surface, you have quasi-particles, they bump to each other and give you this formula. Here, the idea is that actually, to have this, you should have a kind of collective mode which attenuates. You see, think of a wave. A wave propagation by itself can never produce entropy. You need to attenuate the wave to have some dissipation. And what we are finding is that it looks like its attenuation is basically proportional to this thermal wavelengths. Now, one way of understanding it is that in real space, you see, if you think of these guys, these helium-3 atoms, you can have sound waves of different frequencies, but there is a lower boundary. You cannot have a sound wave with a wavelength smaller than the interatomic distance, because there's nothing in between. What is sound at the end? It is a perturbation of local density. Now, the system has two choices between these three ways of creating density, but as soon as you put a temperature gradient, we can break it. So the idea is that what's happening is some kind of sound wave with the largest wave vector with the smallest wavelengths, which is of the order of 2 km. Now, it happens that something like that has been seen. So these people in 2007, so 15 years before we began our interest in the system, looked for zero sum. Because Landau was very proud of one of the achievements of the Fermi liquid theory, the prediction that you have a zero sum. What is zero sum? Is a sound which is different from ordinary sound by the fact that it survives even at zero temperature when there is no viscosity, when there is no particle-particle interaction. And as you can see, they can see. So this is not the first time that they can see, but they had a problem. because normally these things should disappear at higher wave vectors when you have this quasi-particle physics. They saw that actually they can see something. And if you look at their data, you can believe that there is something, there is a peak, so zero is here, and there is this collective mode, this is a collective mode. But after this paper was written, since this idea that you can have a sound wave in the particle hole region was disturbing, they received a comment. The comment was that, look, your mode here, this broadening is almost the same as the frequency. So they put new data points. Now, what does this point tell us? These 2 points are telling us that actually in this region, which is exactly 2kF, actually, so you have an overdamped mode. The energy is basically zero, but the time scale is almost the same as the frequency. This is called an overdamped, and you can see this is 1.88, so it is somewhere here. You see that this mode between 197 and 1965, it is very broad, but its distance between zero and the peak is smaller than the width of the mode. So, okay, we call it a 2kF rotor, but then this is actually, when the paper was published, I discussed with a colleague of mine, Henri Godefroy, who is in Grenoble. I said, what are you talking about? We have already seen this. We talked about this collective mode and the fact that this thing should exist in gravity. I said, but Henri, we're talking about 2D. Anyhow, this was known. Somehow something, the whole idea that there should be a collective mode, and this collective mode has been seen, and there's seen some 2kF, looked like an evidence. Okay. The whole thing is that it seems to matter for thermal transfer. How about theory? Actually, this is a calculation for helium-3, and you see that the whole point is that they are seeing some, again, anomaly here, but it doesn't go to zero. So let me just finish with this helium-3. So what we are trying to understand is that in a solid, you know what is the dispersion of an acoustic function. But textbooks, I don't know, Ashraf, Kittel, they show you up to here. If you go to 2 pi over A, of course you will have exactly, because this is a Fourier transform, you should have a minimum here. No, this is a solid. In a liquid, you would have something like that. In a quantum liquid, you will have something which is soft, means that at finite temperature it's like this, but at zero temperature it becomes like this. And since these two numbers, 2kF and 2 pi over A, are the same, you cannot distinguish between these two. So this is just, it has been overlooked as the possibility that you can have a kind of collective mode in a spherical Fermi surface like this. But again, this doesn't make the matter solved. All of this makes it more plausible. Okay, I'm going to finish my talk with an epilogue, because I talked about helium-3, but you say, okay, who cares? You know, when I talked about this, I was very excited to a friend of mine, American theorist. He told me, Kamran, what you are talking about is interesting, but unfashionable and unfoundable. Nobody's going to be interested in solving mysteries of helium-3 50 years ago. So, how about metals? First of all, actually, people have done theoretical calculations and they found things similar. So this group is the same. Takada did this like a few years ago. So the whole idea is that actually, if you have interactions, you need a high degree of interaction. You find this QKF anomaly. This has not been seen experimentally. It is much harder because you should take care of. The second is that actually, collective excitation in metals become fashionable. No, this is a work looking at plasmons by Peter Abemonte, who finds that actually there is a collective excitation, but actually he didn't look at 2kF. He looked that there is a gapless plasmon in these three materials, which is not expected if there were not multiple Fermi surfaces. But I think our colleagues are going to look at this on 2kF. But let me finish on my understanding. You know, okay, I talked about RuO2. This is RuO2. This is WP2. We know that there are chi-square resistivities, but if you have a weakly correlated metal, the deviation is upward, which is completely normal because you are going to see phonos. I am just showing all of this stuff. This is the chi-square resistivity in weakly correlated metals. Not only we can predict the amplitude if we know the Fermi temperature, we can also say that at some point they are going to stop and give you this exponent of resistivity, which is larger than 2. This is antimony, tungsten diphosphide, copper, or tungsten, molybdenum. So this is well understood. But then, how come that this is not the case in strongly correlated systems? So UPT3 is the fermion on which I did my PhD. Chi-square resistivity is well, but it happens only at very low temperature, and below 2K. But you can fit the whole data with this expression I am giving. In 1 minute, I'm going to tell. And it's not just one system. This is heavily doped LSTO, which is our data actually. There is a downward deviation. And this is stoichiometry, in which we know everything. So here is what I am going to propose and end my talk, is that actually, as you can see, in all 3 cases, we are using a fit which is much better than T-squared. With this guy, it has no other justification than imagining that, like helium-3, instead of having just disorder plus quasi-particle, you have disorder and the parallel conduction by quasi-particle and stunt. And this stunt has something like P-2. So it could be just an accident. The good news for this is that if you put yourself in this situation, there is no need for unclad events. So we will solve another mystery. But of course, all this part is complete speculation. So I finish my talk with this. The first message is that, well, you will be surprised. I was surprised to see that helium-3, actually the quasi-particle transport is negligible when the temperature is above a very small fraction of the Fermi temperature. That we believe that the most plausible source of this discrepancy is that there is a sound mode, which is hydrodynamic, which carries most of the heat, even when you are at 1/10 of the Fermi temperature. Maybe this mode is operating in metals. We don't have a good theory for it yet, but if it is true, then there is no surprise that you have a strange exponent sometimes in metals, which is not 2, because if you play with the 2 parts, you can find any kind of exponent you can. Thank you for your attention.
Which is precisely what you said, that commented on in the end, so that's square root of T resistivity. But these are power law things, so you need quite a large temperature range, I guess, to talk about this as a power law. Can you comment on this?
Yes, so in LSU, actually, as you can see, if you take just T-square, because you see this exponent, this thing will always give you T-square at low temperature. The T-square behavior at LSTO is somewhere at below 60K. Okay, I think even less, 40K, I don't know. But with this formula, you can go up to almost room temperature. Okay, but it could be an accident. So the only statement I can make is that in all strongly correlated systems I know of, again, there is no exception. Take uranium 10 the deviation from T-square resistivity is downward, which means that you have more conduction. So this is actually, when I discussed with my theorist friends, actually, many of them told me, 2KF, everybody knows, you begin with Lindhardt, you have a singularity at 2KF. And this can, but as far as I understood, all of the scenarios were about more scattering. So the main point here is if somebody is there, in addition to quasi-particles, it is not a source of scattering, it's a sort of more conduction. Very much like phonons conduct heat. Now, you can tell me the following. Well, what you are talking about, so we had this discussion with, for example, Andy Millis. So, but what you are talking about is neutral. so it can carry heat. But what about, it's like a charge density wave. Can it carry charge? And then immediately he himself found the answer. We have sliding charge density waves. These are neutrals normally, you have. But since electron hole asymmetry is always there, you need just to have not perfect asymmetry, it also can carry charge. But again, I would like to make a distinction between what is clear. In the case of helium-3, I think we have the answer, but we don't understand. In the case of metals, it's just another fit.
I have a question. Don't they have T2.5 in the temperature in the low doped regime of high TCs that they attribute to variable range hopping?
Yeah, but you see, that is a decreasing conductivity.
Yes.
Yeah.
Yes.
So you have 1/2
It's increasing resistivity that comes.
Yeah. So this is in up. It's 1/2. The exponent is
Yes.
a 10, but it is increasing conductivity.
Yes.
So, and again, I think.
And can it be any connection, any parallel that?
Well, the way we understood it for thermal conductivity was mostly about this. The 1/2 is coming from the Dobroi legs, which is,
yes,
this is just a thermal broadening.
Yeah.
If you have it. There, it is variable range hopping.
Yeah.
The physics is different. But not that you are saying.
It's even to 1/3, I think.
You can have 1/4 actually, and 1/2. You have different fractional exponents.
Yes, there are different
but
exponents.
The fractionality of exponent has a different origin.
Okay.
And yeah, so the epilogue on metals, please take it with a grain of salt, because no. But I think, you see, I know that Lars, this is one of the reasons I'm visiting. Lars is interested in collectivism. The whole point is that collective modes as a source of conduction, not only as a source of scattering, require a visit, because this is something which is really like, and I think if it matters in helium-3, why we should rule out it in other systems? Because the only difference is the microscopic interaction is different, of course. There is no Coulomb interaction in here. But the quantum part is similar.
You told me to take it with a grain of salt, but I'm nevertheless intrigued by the analogy between the behavior in liquids and in metals that you see. So the disorder part, that's fine, but why would it? Why? To me, the systems are exceedingly different. Which solidity must somehow affect the propagation of sound, if you like, through the material in some way. So
we are talking about two types of sounds. So the metal, you see, the metal as a solid has its sound, which are phonons, regular phonons. Now, but you see, the main message is that when you use the word Fermi liquid, you are not talking about the gas of electrons. You see, people use the word Fermi liquid without minding the fact that as soon as you pronounce the word liquid, the liquid itself has sounds. And what I'm saying is not that surprising. Think about the Wigner crystal. Okay?
Yeah.
You are familiar with the Wigner crystal. Wigner crystal has phonons, plasmons. So the question is, does Wigner crystal have an acoustic phone? If yes, I can say no, not in 3D, but in 2D, yes. But anyhow, if you have phonons in your Wigner crystal, if you melt it, and you are still in a region where interactions are important, where are those modes? I'm talking about those. So it is more complicated to distinguish them with phonons of the solid, but they should be there.
Yes, but I don't want to monopolize the others if there are more first. For the quantum liquids, I always thought of something, and now when you evoke the Wigner crystal, it makes me think. If I take a 2D electron gas in a perpendicular magnetic field, you will have the Wigner crystal and you will have the bubbles with 2 electrons per side forming a super Wigner crystal, or 3, and so on. And I was always thinking you could melt these things in different ways. You can melt, if you melt the Wigner crystal, you have individual electrons carrying things. If you melt the bubble, maybe you are melting the connection between the bubbles, which is the superlinear crystal, but you will still have transport being carried by two particles, which could be the 5-half and the 7-half described by the fermion, because it's a paired state. If you go to the bound states with the 3 or 4, you could go into parafermions. So it could be that you have a solid, which is a more complex solid, and by melting, you are still preserving a different kind of individual particles that could be giving different exponents.
Yeah, you see, you know that people like Steve Kivelson have talked about nematicity and all this stuff. So
this is also there in the quantum hall,
exactly,
definitely.
exactly. So you see, maybe my main message is the following. Classical physics, the separation between the three phases of matter has been source of inspiration for quantum physics.
Yeah.
But somehow there is something which is a little forgotten, is as soon as we talk about a liquid, even an ordinary liquid like water, there should be some discussion of phonons there, phonons of the liquid. No, maybe they don't matter that much. And I think Landau's main message is that if you go to sufficiently low temperature, doesn't matter. In a quantum Hall liquid, because which you have more degrees of freedom and interactions are important, and of course you have this. But yes, as soon as if you reach the Wigner crystal, at some point you should ask yourself, during the melting, what happened to the phonon?
Yeah.
Because it doesn't go away.
There is this thing that the roton becomes the phonon of the solid, right? So that is also something I never understood very deeply.
But you see, this is really the roton. Actually, there is a very good, again, you find one of the guys who has written this, Nozier, he has a paper about rotons. He says that this is a misnomer and why it is like a charge-sensitive wave. So people, a lot of this knowledge is like diffuse, available. But so I'm not saying that there are phonons in liquid. It's not a discovery. It's just like nobody, as far as I know, has thought about how they can have a conducting behavior inside a quantum liquid. This is maybe something which is but the other aspects is just recollection.
May I suggest that we break the discussion here and continue it offline?
Thank you.
Yes, thank you.